Итак, следующий доклад. Давайте посмотрим теперь на опыт наших коллег из Германии. Это доктор Jörg Jungwirth и Макс Rottensteiner. Пожалуйста.
So, thank you for the introduction. Good morning, ladies and gentlemen. It's a pleasure for us to be here today in St. Petersburg to present some of our projects we have carried out during the last years. Now, how does it work? Yeah. Here we are. For the purpose, we have prepared a large variety of projects we will present today. We present just a brief introduction of every project and then point out how the project was modeled and what in detail was the analysis that was carried out for each project. We have subdivided our projects, or the presentation, we have subdivided the presentation in 5 issues. There's in the beginning metro projects. We go on to tunnel projects. There's a third part with bridges and viaducts. Then we have a very specific issue, dynamic analysis. And finally, there will be some arenas and stadiums. The presentation we will have together, I will have together with my colleague Max Rottensteiner. And we'll hand over from one side to the other during the presentation. But let me just start with a very brief introduction of the company, SSF Ingenieure. What's the German name? So it's not engineers, but SSF Ingenieure. We are a Germany-based engineering firm, structural designers. We are working in almost all domains of the building design, starting with, well, buildings, of course. Then there are all structures in the context of traffic infrastructure, so bridges, tunnels, retaining walls, and whatever comes with this. Then we have some special engineering geotechnics. This is a very big issue also for us, everything which is concerning foundation, deep excavation pits and all these. Environmental engineering is a very big issue for us today. And as I already said, infrastructure is a main focus of our company. Here we are. Just to give you a little bit of an overview of the markets we are working in today. It's a little bit spread around the world, starting, of course, with Germany and Europe. They are more focused in the Eastern Europe countries. Then you see there is a main and northern part of Africa. And finally, worldwide, the emerging countries, the BRIC countries, so Brazil, India, China, and Russia. These are very important markets for us. As I said initially, we are working a lot in traffic infrastructure. And for these emerging countries, I think this is one of the important facts for an upcoming country. When the economy is rising, the requirement for traffic infrastructure is an important issue. And that is why today it's very interesting for us to work in these countries. What kind of services we are providing? We are providing service of construction from the very initial phase, so feasibility studies in the very beginning, to over all the phases of a project, to finally implementation design. We have some special issues, as I already said, well, traffic infrastructure, geotechnics. Today also building information modeling is a very important issue for us, and check design. And the way we are working today is in a kind of a network. We call it SSF Group. We work together with a lot of partner companies, locally in Germany, but also worldwide. We have subsidiaries today in many different countries. There's China, there's Greece, there's some of the Eastern European countries where we are situated. And that is what we realize today is the best way to offer service to our clients, that we have a network, we can work in all disciplines of engineering, working together with local companies, also with local companies here in Russia. That is also a very big and important point for us, to realize mutually, so together with all these partners, our projects, and to supply to our clients a good service. Now, we'll come immediately to the projects we're starting, and there I will hand over to my colleague immediately. We're starting with underground structures.
Okay. Now I will show you some underground projects from SSF. The first project is two subway stations in Delhi, in India. We did the design for the two stations Malviya Nagar and House Cars. The client was the Delhi Metro Rail Corporation, and the construction costs were about 120 million euro. Our services were the preliminary design of the subway stations, the definitive design of the subway station, and also the construction design of the subway stations. We calculated the stations with TEDdy, so we wrote the text input. We didn't work graphically in this case, and we used also the CSM manager, the construction stage manager of SOFiSTiK. Here you see the construction site on the left side, and on the right side the cross section. And here some screenshots of the animator of SOFiSTiK. And this is now a very short video tape where you see all the different construction stages. It was necessary to model all the different construction stages to get all the frozen internal forces from one construction phase to the next one. I show it quickly again. You see on the top, you see the struts, the horizontal struts, and then the struts in the lower area, and then all the slabs and the columns in the middle of the station. So that was the first underground station. Now the metro station Marienplaz in Munich in Germany. It's an existing station, and there was done a widening of the platform level. It's a very central, not in Munich, so there are a lot of interfaces with a lot of other structures. The main problem was the historical building on top of the underground station. There is a historical building on top of it, and the deformation, we had to be aware that deformations rise not too much during construction. In this case, we also did the feasibility studies, the preliminary design, the tender design, the detailed design, the geotechnical design, and also the interface management. Here you see the construction. Marked in blue, there is the tunnel U3, U6. This is the existing tunnel marked in blue. And the yellow part is the existing structure of the underground station. And marked in red, hatched in red, there is the widening platform. It helps to get more people out of the station because of the high traffic here, in this case. And here on the top, here you see, this is the widening platform, the new structure. Here again, the historical building on top. And under the underground, you see the pilot tunnels. We had to make some pilot tunnels for the soil freezing. We had to freeze the soil on top of the platform widening to get lower deformations. Here again, the structure. The Munich City Hall is the historical building. There was done a start shaft you can see it on the right side. Then the pilot tunnel for the soil freezing. Then there were made the soil freezing. You see it hatched in red now. And then under this soil freezing, they excavated the new platform, the new widening of the platform. And here you see now all the breakthroughs. The breakthroughs are from the widening platform to the actual platform level. This is now the final state, how it looks today. This is the widening platform, and behind these black breakthroughs, there is the actual platform level of the underground station, of the underground line. The construction costs were about 25 million euro. Okay. Oh. Sorry. Here you see the breakthrough. The breakthrough was pretty complicated. First, we had to break through just one part. You see it on the left side. Then they had to pour the concrete and then open the right part, and then the whole structure was done. First we made a 2D model with Talpa, and it's a 2D section of the tunnel to see all the 2D problems. But then when it comes to the breakthrough, it's a 3D problem, of course, and so we had to extrude it in 3D and see all the stresses in 3D. And this you see on the right side. Now the model, you see, here you see the part in the middle, and you see the construction phases. First the cuts, the breakthrough, then the new concrete around, then the column in the middle, then the next breakthrough, then the concrete structure, and then the final state. And on the left side, on the top, you see the pilot tunnel for the soil freezing of the widening platform. Here you see the breakthrough in the construction phase, and on the bottom you see the widening platform marked in red. Okay, now the last underground station. It's an underground station in Algiers, as the station des Ateliers in Algeria. This is a more recent project, and here we are also currently working on this project. We model this now with Revit. Revit has the interface to SOFiSTiK, and you see it also on the on this screenshot. Or you will see it on the next slide. Yeah. It's very nice that you get immediately cross sections. As you can see here, you just shift the mouse and you see the cross section of the station. And out of this 3D model, you get the drawing. Of course, you have to add something, but you have the main cross section you get out of this model. And with this model, you can also make the calculation immediately. So it's all in one. You see, SOFiSTiK is also implemented in this Revit 3D. You see on the top, you see the SOFiSTiK button. You just push the button, and then you can export all the 3D model to the SOFiSTiK calculation. If you make a change in the Revit 3D, you get immediately also the change in your calculation if you want. It's the so-called BIM system, the Building Information Modeling. Here you see the animator. It's exactly the same model, just exported to the SSD. Here you see some screenshots of the station. And here again the interface. It's building information modeling. As I said, you have this one 3D model, and of this one 3D model you can export formwork plans, structural analysis. And if you make changes, everybody sees the changes. This is the idea of this Revit. Here you see also a short video just to see that how the model works. This is now the normal SSD, the standard SSD from SOFiSTiK. You can use all your features that you have in SOFiSTiK. You can also add something that you don't have in Revit if you want. Okay, And now I come to the tunnel project. The first tunnel is the tunnel in Gdansk in Poland. We made also the feasibility studies, the preliminary design, the tender design, the detailed design, the geotechnical design, and the interface management. I don't show you all these different phases. I just show you a small analysis about the deformation of the tunnel that we also did. These are the analyses we did with SOFiSTiK Teddy and with the software WinTube 3D from Fides. It's a special software to get 3D tunnel problems solved. Here you see the the main problem of the tunnel. It's a tubing tunnel with segments, and all the rings are a bit shifted to each other, and so you have different. So the joints of the different rings are not in the same place. So it's not very easy or not possible to get a clear deformation just with a 2D section. It's better to analyze a 3D section. Here the model on the bottom, and here the problem again. We have here some vertical springs, and here the rotation spring. This is one ring, and on the next ring you see that it's of course shifted. And if to get the deformation of the whole tunnel, of this whole structure, it's better to analyze a longer part of the tunnel to see how it reacts, how the vertical springs act, and how the rotation springs act. Therefore, we did this in 3D. This is the soil model. There were some very high loads on top of the tunnel because it's in the area of the harbor in Gdansk, and there are some heavy loads because of freight, because of the harbor. And so we had to consider these high loads, and therefore we had to analyze the deformations very precisely. You see again a short video. Here, this is just the soil, then the tunnel. Then you see the tunnel in the middle here, and then just the tunnel to show how it looks like. And in the middle of these tunnel rings, you see the four rings. In this case, there are these gaps with these springs, and all these springs you can then also change and vary in the SOFiSTiK in Teddy. You can use directly Teddy to change and to analyze all these springs and the deformation, of course. Okay. So that's now sending a tour. It's also a current project. It's a redevelopment of the underground station. Here you can see the existing station, and here the metro tracks. And here on top you see the new structure. There has to be done some new entrances because of fire and safety reasons, because it's also an underground station in Munich where there is a lot of traffic, and so they need more entrances and exits. Here there will be two new entrances. SOFiSTiK model calculates the whole new structure, but I just show you now this small part of our calculations, just this breakthrough from the existing tunnel to the new structure. In this case, we also modeled the 2D model in Talpa to analyze all the historical construction steps to get all the frozen internal forces in the inner lining. And then we took the radial spring forces from the 2D model and put it as a load to the 3D model. So we have considered all the construction steps before in the 2D model, and we have it all in the 3D model too. And then in the 3D model, we did the breakthrough. We will also use soil freezing on top of the tunnel to get the breakthrough watertight. There we have the problem that the soil freezing causes expansion, and this expansion is not very good for it's very bad for the existing old tunnel structure. And we had to analyze, or we have to analyze, that the inner lining from the old existing tunnel carries the load of the soil freezing. The soil freezing is also modeled in SOFiSTiK just with temperature. We used a rise of temperature to get this deformation, deformation because of soil freezing. And then we also changed the material in this area, the E modulus in this area, regarding to the soil, to the frozen soil. It has a much higher E modulus. Here you see the video of the 2D model. Here you see, it was done in NATM. It was first they cut. It's 40 years old, the tunnel. So this is an old structure, but we still considered also the old breakthrough of the old tunnel to have all the loads that are inside the inner lining. This is now the outer lining, and then the inner lining comes. And this is now the new excavation pit that we are doing now. And now you will see the soil freezing. And then the breakthrough. The breakthrough, this load case is, or this construction phase is not possible to analyze in the 2D model. It's just shown here to show it, but we didn't analyze it, of course, because this is not possible in 2D. Therefore, we use now our 3D model. This is this 3D model. So we have now all the loads of the 2D models on top of this 3D model. You see the deformation on the model. And here we made a breakthrough in 3 different steps. And this is now the final state of the new tunnel. For the 2D, we used the TALPA, and we used also the CSG, the construction stage manager for geotechnics. So you write an input file, and then SOFiSTiK calculates automatically the different construction phases. And there, in this case, for example, the soil freezing, it's not so common, and therefore it's not you cannot put it on the you cannot put it immediately in the input file, but you can write it manually after you have calculated all the construction steps. You can also put it manually inside the model and calculate it again. So it's very useful to have also TEDdy, the text input, to make some changes on the model if you want some very individual changes. Okay, now I hand over to my colleague.
Thank you, Max. Now, thank you. Well, now we are leaving the underground. We are getting a little bit higher, up in the sky even, with some bridge and viaduct projects. I get started with a bridge over the Eisel. It's a bridge project in the Netherlands. It's a bridge about almost 1 kilometer long. It's a red bridge, indeed. It's not the other 2 or 3 bridges over the same river. It's a red bridge in the very front. It's a railway bridge carrying high-speed railway, 2 tracks. And well, as you can see, there's a midspan in a very specific style, architectural style. Midspan is about 150 meter wide. There are 2 side spans with 75 meters, and then there are, and I think in total there were 19 spans for the whole bridge. Yeah, well, this is a competition. It was a competition that initially started as an architectural competition. The architect is Quist Wintermans from the Netherlands. It's a long-term partner of ours, so we are in quite good contact with them. And already for the very beginning of the project, we were working together with him to work mutual together with an architect to develop the design of the bridge. So over several stages, like for a bridge competition, we do develop the design. The initial idea was, or the architectural idea was, to adapt the design of the bridge as good as possible to the Netherlands environment. And as you know, Netherlands is very flat. I think the highest mountain is something like 60 or 100 meters high. So we really try to stay very flat for that bridge and not have a very high pylon. Well, as you can see in the initial design, there were some pylons, but then very soon we decided, well, that must be a very smart and smooth shape. And we finally came to the solution of that arched truss structure. So a round curved shape, including arch, not being very high, to not overcome over the terrain which is around. In addition to the bridge, to the rail bridge, you can see there's a footpath on one side, which is just cantilevered to the bridge. This competition ran then over several phases, and finally we had the chance to develop together with the architect the project, and then later on with the construction company, which was Süblin and Donges in that case, to run the project and go through the implementation of the project. So we had the chance to go through all phases of this project and participate in all phases of the project. Now just seeing the alignment, you see the approach bridge on one side slightly curved, but the rest of the bridge is almost straight, although the vertical alignment, there's not really a very steep ramp going up or down. So a continuous girder from the structural point of view over the whole length. There are only expansion joints in the very end of both sides. Maybe in this case I also have to mention on that bridge we have, in addition to the high speed, which requires very small deformation, so very high stiffness for the structure, we have in addition a switch, so a turnout, and therefore turnout, it's impossible, high-speed turnouts, it's impossible to have any joint in there. So the whole bridge is only one girder continuously running over the 900 meters. Then from the structural point of view, well, of course it's an arch, but if you have a closer look, and I will try to use that theme, you will realize it's an arch, but the arch is ending in the mid of a span, which is not typically logic for an arch. It was an architecture competition, we had influence, but however, this is a kind of strange. But as an engineer, you will of course find a solution to handle this. It's still an arch, but the arch is working over the diagonal, the second diagonal here, and the second diagonal on the other side, and then in the upper chord. So it's a straight kind of arch, but still it's in a certain way working as an arch. The advantage of this type of structure, because then you have the rest of the arch in a certain way as a cantilever for the side spans, which are still 75 meters, and that enables to have that side span without any additional other support, and it's still stiff enough to carry the load of a high-speed railway. Just going to the cross-section, this is a cross-section of the approach bridges. In longitudinal direction, we have two box girders on both sides. Then you have transversal girders, which are carrying a concrete slab. And then on the concrete slab, you have the ballast and the railway finally. As I said before, on one side, there's on cantilever pedestrian bridge. And finally, this pedestrian bridge works the same way. There's a concrete deck, and there are two longitudinal girders, steel box girders. Now, this section, the main section of the main bridge, the cross section of the main bridge, there, in addition to these two longitudinal box girders, we have these arches, these truss arches, and you have the upper chord, the diagonals, and the lower chord. Now, when it comes to modeling this bridge, as we heard before, the initial step is, of course, understanding how that works. And that's what I initially explained. It doesn't really work as an arch, how you can see it, because the end of the arch is in the middle of a span. It works in a different way. And that you can imagine these diagonal parts, they're really very highly loaded. They are steel plates, 80 millimeters, to take all the stresses. This is a very big part of the load, which is just going down there. Now for the modeling, well, it's a bar structure, so it has been modeled as a bar structure, in this case with SOFi MSH-A. And in addition to the model bar structure, we added for all the nuts a finite element mesh. This has been done in order to have the possibility to take the correct stiffness of these nuts to the whole system. On the other way around, this kind of modeling has also the advantage that for the local dimensioning of every nut, we get the forces, the internal force, from the whole structure automatically out of the system, and then can put it on every element. Yeah, that is the way how the total model works. Here, you can see in the first step, it has been modeled without taking into consideration every single knot. And then the model was recalculated, taking now into account every single knot as a finite element calculation, and having then all the internal force and stresses in every knot. As you can imagine, for these kind of bridges, construction stages are also an important issue. Well, for the approach bridges, it's not too complicated. You can approach this easily and put with a grain your steel structure, prefabricate it, and weld it on site. But then for the central part, 150 meters of span, the central part was prefabricated onshore, then put it on barges, swam in the right position, and then with hydraulic checks, pulled in the correct position. All these construction stages have also been calculated in the SOFiSTiK model and calculated with this construction stage manager. This is how this final closure of the middle gap looks like. That's a huge thing to see how this works, to get in reality, as we had before. It's not only modeling, but when you really see what happens on site, this is another scale, and it has to work. You have to be sure that all the forces are correct. And well, that is how it looks in final stage. I think a very nice, interesting project. And well, in the end, finally, SSF, together with all the consortium, we also won a prize for that bridge from the Netherlands, the National Steel Prize. I will immediately step to another important bridge project. This is now on the island of Mauritius, in the crossing of the harbor of Port Louis. Here we have downtown Port Louis. It's not really a very big village, but it's capital of Mauritius. And as you can see, right now the main road is just passing through the middle of the city, exactly at the seafront where you normally want to have pedestrian walkways and all these. But now, right now, there's big congestion, a lot of traffic there, and everything is blocked in the morning and the evening. So the project was initiated to have a bypass crossing over the harbor. A crossing in the back was not possible, or is not possible, because there are huge mountains, and you will not, well, it's not able, you need a tunnel to get there. In addition to the constraints we have now from the environment, it's in addition that there are nautical restrictions. We have to have an open corridor with a height of 50 meters for big ships passing in the harbor, and a width of 270, 300 meters, something like that. So the chosen solution was a cable-stayed bridge. The cable-stayed bridge was one harp of cables, one layer of cables in a semi-harp pattern, and a diamond-shaped pylon. Here, the span arrangement, the final opening in the middle was almost 1 kilometer, with on both sides back spans and then some approach bridges. So in total, the bridge is about 2 kilometers long. For the 3 different sections of the bridge, we have chosen different cross-section, a standard box girder and reinforced concrete for the approach bridge, so a standard system. And then for the main bridge, we have 2 parts, the back span, where we need quite a lot of weight to counterbalance the midspan. And for the midspan, we have chosen also a concrete, and that is a little bit specific for this type of bridges. We have chosen to take a concrete deck. Concrete is quite heavy for half a kilometer of span. Of course, this is quite a challenge, but this choice has to be done because of the boundary conditions on that island, the island of Mauritius. I don't know if you know it. It's, I think, 80 kilometers wide and 40 kilometers long. So it's really a small island. On that island, everything what you want to construct in steel, you have to import it. And on the island, you don't have any contractor who's able to handle steel and to produce some steel elements. So everything, if you would have done it in steel or in composite, everything would have been imported and produced somewhere else. So the choice has been done. We will do it, however, in concrete, even if for a half a kilometer of span, this is a quite heavy solution. We try to reduce as much as possible the section. As you can see, as we compare the section backspan, we wanted to have it heavy for avoiding uplift. And the front span, we really reduce all sections to the minimum. And in addition, we have internal, on the inside, some steel elements to take tensile forces and distribute the load over the width of the bridge. Now it's blocked. Now it's reversed. Okay. Now for the pylon, as I said, it's a diamond-shaped pylon, also in concrete. And there's something very specific with this pylon. We've chosen not to use any bearings between the bridge deck and the pylon. So finally, it's an integral structure where we can avoid these elements. You know, bearings for this type of bridges, they're very heavily loaded and they normally demand a lot of maintenance. In that case, we have chosen this because we, as I initially mentioned, we had to keep a height of 50 meters over the terrain. So the legs of our pylon, they're 50 meters long. And in longitudinal direction, where we will have a lot of deformation due to temperature and all other loads, we can now handle this deformation just by deforming the pylon. That will create a certain constraint stress, but this stress is not so high. So we have chosen a solution, an integral bridge, to reduce maintenance costs in the future and, however, handle internal forces. Now, how it was modeled, this project was modeled very basically with just the model. Well, in the beginning we had a star model from SOFiSTiK. Then we changed over to SOFi MSHC, where we had the chance to directly model the shape of the bridge following the alignment of the road. A very specific and interesting point with cable-stayed bridges is the form finding you have to do in the very beginning, because if you would install the cables just on the bridge in their initial length, you will have a very big deformation due to dead load. So you have to tension and to pre-tension every little cable to put the bridge in the correct position and to have equilibrium of the forces. For that bridge, as it is now internally statically indeterminate, as well as externally statically indeterminate, as it is an integral bridge, this process, which is an iterative process, was pretty complex. There's a module in the SOFiSTiK software where you can use an equation solver to solve this kind of problems. But as this was very complex for this bridge, we initially used that solver, but then later on we just manipulated it a little bit by hand finally and did some iteration to get the best distribution of the internal forces. Well, then, of course, loads have to be applied. There are dead loads, tensioning forces of the cable, settlement of the piers, temperature. Oops, that was the wrong one. Here we're back. And then, of course, traffic load. We were just running over the whole bridge to finally get the envelope of the moment for the bridge deck, as well as for the pylon. And if I just go back, you will again immediately realize that here at the connection between bridge deck and pylon, there's something very special. That is indeed exactly what I said before. We have an integral bridge direct connection, so there is a moment, the bending moment, going from the deck to the bridge, what you will normally not find for a cable stayed bridge with a bearing. The second big challenge for cable stayed bridges are the construction stages. Because, of course, this will be erected step by step. Well, in the beginning of just the approach bridges, when you reach the pylon, everything will be erected in free cantilevering, putting always one cable, one segment, one cable, one segment, one cable, one segment. And now, in order to achieve finally the correct position of the bridge deck with the correct stresses in the cable that we have calculated initially with that form finding process, we have to do a back analysis in that case. So we deconstruct step by step every construction stage backward. So we take off every cable, one section, one cable, one section, to find out which force we have to introduce in every single cable for the construction of the project. There again, the construction stage manager of SOFiSTiK is very helpful, because there you can automatically do these steps backwards. This project has also been done together with an architect, and we are now at the process where these documents are handed in to the client, and it's a tender process where now the project is mandated to the client, and we hope to be able to continue this project also for the construction. Maybe just one specific remark. By the cooperation with the architect, suddenly we had a restaurant on our pylon on the very top in 110-meter height. It was something new for us, but I think it's a good thing to valorize such a bridge. It's probably the first bridge who will then have a restaurant on top. If this will be constructed like that, carried out like that, finally, I'm not sure, but we will see. It's an idea to have also a touristic effect for our bridge. And well, I will close the bridge part of our presentation now with a inside of a little bit of our Chinese projects. We have been carrying out a lot of projects in China during the last year. We did a lot of consulting work over there, and this is one of the projects. It's a big bridge over the Yangtze River. The name is Dezhongguang Bridge. For me, it's still impossible to pronounce it the correct way. Chinese always get laughing when I try to pronounce the name. That's why we in general just call it the Big Bridge. The Big Bridge, why? Because, well, this is a Yangtze River. Maybe you've heard it's one of the biggest rivers in the world. And so is this bridge, because, well, from the picture, it just reminds to the bridges that have been built in the 1950, 1960 in the US. They have a lot of these kind of bridges. Today, you wouldn't really design a bridge in that way. That design has been proposed by our colleagues in China from the SSTI, Second Service and Design Institute. And now, if you come to the scale of that bridge, the opening is 336 meters, 2 times. Then there's another span, 200 meters. So it's really a scale where you normally wouldn't have a bridge like that. This is really, in a certain way, out of scale. So I think it's also the reason why finally the Chinese came to us and asked us for check design for that project. And we said, well, looks a kind of strange, but okay, we will try to handle this. What has to be mentioned? Well, it's for their high-speed railway network. This is for the line between Beijing and Shanghai. It's 4 lines of high-speed railway plus 2 lines of metro. So there are 6 lines of railway running over the bridge. Again, out of scale a little bit. The 4 lines high-speed are running inside the girders, and on cantilever on both sides, the metro lines are running. So when it comes to modeling, well, of course, it's a truss structure. It's an arched truss structure. we don't only have one layer of these, but we have three. There's on both sides, and in the middle another layer. On the diagonal view of the SOFiSTiK model, you can already have an idea of this. But when it goes into detail, of course, we have all the diagonal reinforcing bars between the layers. And so you can imagine for this bridge how many bars are in there and how many input data had to be handled. Finally, we had 4 main consulting tasks for the bridge. That was in the first just a stress analysis to assess which of the bars are at their limit, if they're plastified. Of course, we had some bars which were plastified in final stage, close to these middle piers. You can imagine the big forces from 336 meters of 4 lines of high speed. You will collect a lot of forces, and so there were some bars who were not able to carry the load, but they just had to be exchanged by a bigger profile. Another consulting task we had to carry out is assessing the construction phases. There we were really very surprised because our Chinese colleague told us we were just calculating that bridge in final stage. They just did enter the model in final stage, and they didn't consider at all construction stages. And you can imagine, for free cantilevering the 330-meter arch, so it's 160 meters from each side, there are enormous forces. They finally had to be handled with temporary pylons and cables to enable the work of these. And it's not only the stresses that will occur during construction, but it's also a big deformation you will have. And so that was very, very surprising for us. They just said, well, we calculate final stage, and when we have a deformation in the end of the construction for closing the gap, we'll just put hydraulic checks, check the arch in the back in the initial position without any loading, and then we put the last bars in the middle and we connect it. And that was the idea how they intended to finalize the arch. We had another solution. We just proposed, okay, put away for the free cantilevering your bridge deck and your hangers, so you save already half of the dead load, and then you just install these elements later on, because otherwise you will not manage to handle this project. Further investigation has been done with the bridge deck itself, because the bridge deck was on one side isotropic deck, steel deck, and then on top, for carrying the ballast, there is a concrete deck. So these two are working together, and in order to have the right stiffness for the whole system, we also had to introduce the concrete deck and all the isotropic deck in the total model to verify all the deformation in the correct way. A second task we had to handle with the deck is the fatigue analysis. In that case, we got, in cooperation with SOFiSTiK, we got the load model for the newest Chinese high-speed railway, the CHR3, something like the ICE3, the European high-speed train, German high-speed train. And then we carried out analysis of this composite deck just for one section, where we ran over with that load model, and we assessed the stiffener and the fatigue of the stiffeners. The final task we had is just assessing the dynamic loading of this bridge. There was earthquake. We are just putting here the eigenforms of the bridge, and then the common eddies for the hangers, because as you can imagine, these hangers, they have a length of 90 meters, and with a wind-induced swing of these elements, there will be also very high loading for this element. So the dynamic analysis was finally also carried out for this bridge. That is how it looks during construction stage. I think it's quite interesting to see that picture, because if you consider this black dot up here, it's a person working. So you can a little bit imagine the scale of that bridge. That's really huge. And when you were on construction site, it's never seen a project like that before. The crane we have here is one of the biggest crane you can have on a barge. It's not just a standard crane, but it's really a huge one. And as SSF, we had the chance to be also involved in supervision on construction site. So we could always follow during construction what happened on site. Another picture of construction stage, and that is how it looks in final stage. I think now we are. I was just in the end talking about dynamic analysis. We were going out for the bridge. Now we get again more into detail with one specific dynamic analysis that has been carried out by Max for noise barriers for high-speed railways.
Okay, so this is a bit a special topic. We calculated, we did these calculations because the noise barrier walls were designed for lower velocities, and now in 2013 they raised the velocity to 230, and so the pressure rises a lot, and so we get a lot of problems, a lot of fatigue problems for the noise barrier wall. In the underground projects and in the tunnel projects, we use a lot SOFiPlus with AutoCAD, so we can just draw it in AutoCAD or in SOFiPlus. In this case, I prefer normally to use SOFiPlus because it's more easily to understand what you are doing. But in this case, for noise barrier walls, I always use Steady because it's very complex and you really need a clear definition of all the nuts and all the structures to see, because you cannot see exactly where the loads are going. So it's very useful to use Steady in this case. And the structural system is not so complex to model in Steady in text input. So there we have these advantages that we can use variables and loops and all these comments. And here you see a screenshot of the text input on the right side. First, I just explain you very shortly the general theory. When the train is passing by the noise barrier wall, it causes this pressure. You see on the top in this image, you see the pressure. When on the front of the train there is a high peak, in the middle is a peak, and at the end there is a peak. And these peaks causes these high pressures. And we have, especially we have the problems in the welding seams, because seams are not so strong as the normal steel material. This is a typical noise barrier wall in soil. This is not so stiff, and this is on a bridge, and there the stiffness of the noise barrier wall is much higher, and it has a completely different behavior. This is the detail of the noise barrier wall. Here you can see the footplate, and here this footplate, there are a lot of welding seams, and on the top of the structure, of course, there is the biggest bending moment and the biggest stress, and there's also the welding seam. So here you have the biggest problems. This is now a picture from this track. You see the noise barrier wall made out of concrete in this case, and the piers in the middle made out of steel. Then another image of the same track. There are glass elements that have also, of course, a different behavior, and elements made out of aluminum on a bridge. As I said, the deformations were very high. Here you see the strut and tie model on the bottom, and the finite element model on the top. Sometimes we are using the finite element and sometimes the strut and tie, depending on the question. And here you see the calculation at the right side, and in reality the deformation. I show you the video again. You see that the deformations are very high, also in reality. It's some centimeters that the noise barrier wall moves because of this high pressure of the train. And you see that in reality, in the calculation and the reality, the calculation and the reality are very close to each other. Okay, and now here this is now the output of SOFiSTiK. On the right side, you see the diagram, and you see the movement on the left side of the noise barrier wall. You see that all the peaks are registered, and you can use this later to calculate the actual lifetime of this noise barrier wall. Here we also did some measurements, and as you can see on the bottom, you see the pressure that is measured on site, and you see that the pressures are very similar also to the load that we applied. On top, you see the load diagram. It's very similar to the measurements on site. With these loads, we take these loads, put this in SOFiSTiK, in Dyna of SOFiSTiK, where we can also consider the time. And with this load case, you get, as you can see on the bottom, you get completely different results depending on the eigenfrequency of the noise barrier wall. Noise barrier walls in soft soil have a low eigenfrequency, and so you have this behavior on the right side. You have a lot of post-pulse oscillation. You have a lot of movement after the train passed by. And because of all these peaks after it and before, you have a lot of peaks, and you have to summarize all these damages that are caused by all these peaks. So in this case, you really need dynamic analysis to say, if you want to say exactly how long the lifespan is of this noise barrier wall. If it's calculated, if it's very close to failure. On the left side, you see a noise barrier wall on a bridge, and you see that with a high eigenfrequency, there is not a lot of post-pulse oscillation. So this, in this case, you could also make some calculations that are easier to calculate the lifespan. But for the right side, it's really important to make this dynamic analysis. We use the rainflow method to summarize, to get all the different strains and stresses, all the different stresses in the wall. Then we make the summary, and we get the damage per train transit. As you can see here on the bottom, we summarize all the damages that are caused of every single peak here. And then you get the damage per train transit. Then, if you know the number of train transits per year, you can calculate the damage per train, and then you can calculate easily also the lifespan. In this case, it's here there is the formula. In this case, this noise barrier wall with this behavior has a lifespan of approximately 18 years. It was very important to make these calculations. To keep the noise barrier walls and so they didn't have to knock down the noise barrier walls immediately. Therefore, we made this precise analysis for every single noise barrier wall. For the footplates, we used also SOFI Plus to analyze the stresses in the footplate. From Dyna, we get the load. Oh, sorry. From Dyna, we get the loads. We put the loads on top of the steel construction, and then we get the stresses here in the footplate. The anchors for anchors we put some springs to analyze also the anchor forces. Okay, that was my part. Now I hand over to Jörg again.
Thank you. I hope we still have some time. I'm not sure how we are in the timing. Is it okay? 5 minutes I get. Okay, so we go quickly for the last part. The last part is considering areas and arenas and big stadiums. And I will start with one very well-known building. At least in Munich and in Germany, it's well-known. Unfortunately, it's not well known because of our engineering, but it's well known because of what is inside, which is the delivery center of BMW's cars. Well, however, today I will not focus on the cars, but I will more focus on the structure of the building, which is, I think, as interesting as are the cars underneath. The design of that building, well, finally, you can't really call it a building. It's a big stadium. It's a big hall that is constructed with this. The architect is Kohoff Himmelbrau from Austria. The building is subdivided in, well, of course, the big roof you can see on top. It's kind of floating over the whole, and that's also the architectural idea. It's floating over the whole hall, which is underneath. And then you have on the left side this double cone, which is also a very complex structure, complex shape. And then, I think it's better to see in this cross section, you have underneath a huge concrete structure, which is more like a traditional building. But however, as you can see, it's more than half of the structure which is underground, and only a little part is coming up. They have all their stock of cars down there. There's a big garage where, when you one day will buy one of these BMW cars, your car will be stored until you can get there and get your car. Well, from the structural point of view, well, of course, there's the building, which is underground building, quite complex excavation pit in the beginning. We have very high uplifting forces, so we even had to anchor the whole building downwards to avoid uplifting due to water and hydraulic pressure. And then on top, we have that complex 3D truss structure, which is a little bit also separated in that cone and the roof. For the roof, has also been to mention that the roof is not only from the architectural point of view floating, but it's really floating because there are no pillars in that, no columns in that hall. So it has to carry between the very left side where the double cone is, and in the back there's some concrete structure where it could be beared, and the very other side where again is a conference center, and in between there's no column at all. Calculation has been carried out using SOFiSTiK software again. On the one hand side, traditional finite element for the concrete part, and then of course for the steel part, for the 3D truss structure with a bar structure. This project has been started about 10 years ago, and at that time the tools were not so strong like they are today. This has still been calculated using STAR, which is a simple model for the bar structure in SOFiSTiK. Also, this structure has initially been designed with Revit, but at that time there was not the interface between Revit and SOFiSTiK, so it has to be transferred into SOFiSTiK via Excel sheets with, well, you can imagine the number of bars with a very, very long list of knots and bar elements. Now in construction stage, as an engineer, we have to show it in construction stage because that is what is interesting, because we see the roof and the structure inside the roof. Later on, for architectural reason, there was a cladding and a facade on it. Nowadays, unfortunately, you don't really see that beautiful structure which is inside. It's all hidden behind facade elements. This is a double cone, the lower part of the double cone, complex 3 steel structure. This is, as I mentioned before, a part of the concrete structure where the roof is connected to for load bearing. And now, well, how to erect all these? There were a lot of steel towers, temporary steel towers, to be able to build the roof and to assemble the parts of the roof. And only at the very final stage, when all the parts had been assembled and when it really worked as a truss structure, these steel towers were taken out, and now, well, with very little vertical elements, the roof is floating, and the architect, the idea is more or less floating over the hall. Okay. Here again, as I said before, well, the structure has only been seen during construction because that is how it looks nowadays. it's a beautiful, interesting architecture, but all the engineering which is inside is today unfortunately hidden behind cladding elements. However, I think for the person who's taking his brand new BMW car, he'll be very happy to be there. A last project, I think we are running out of time. Maybe I should just skip that one. And, well, just some words. It was a very interesting project. We ran in Baku in Azerbaijan. We had the chance to build a stadium for the European Song Contest. And European Song Contest, well, you can imagine as the country who won the competition the year before, they have to build a stadium and to run the competition the next year. For that project, we only had 8 months to design and to build the whole stadium. So it was quite a rush and quite a challenge from the timing. I'll just go through and take finally the occasion to give a little bit an outlook. As we're here today in St. Petersburg, I will give an outlook on one project we just started to work on, which is the Zenit Stadium here in St. Petersburg. It's a soccer stadium for the local team. Well, probably you know better than I how good that team is in soccer. I'm not aware of the team that will play in there. We did some first analysis for this stadium, and we would be very pleased to continue also our work here in St. Petersburg. And that is also why we would be quite open and interested in having discussion on these kind of projects, on the projects in general here in Russia. So that is, as I said in the very beginning, Russia, I think, is a very interesting market for the future. There will be a lot of projects in the future here that I think is a very challenging work for all of you, the engineers who are working here. We would be happy if we could be a partner and cooperate on this kind of project and have the chance to continue not only our presentation here today, but continue discussion and cooperation with you in the future. Thank you.
Спасибо большое. Коллеги, мы прослушали 2 интереснейших доклада, посвященных программному комплексу SOFiSTiK и достижению наших коллег из Испании, доктора Угора Короса и доктора Jörga Jungwirtha и Макса Ротенштайнера. И мне бы хотелось, прежде чем мы сейчас уйдем на кофе-брейк, буквально пару промежуточных таких выводов сделать по нашей вступительной секции. Мне очень понравилось лично то, что было замечено и в первом, и во втором докладе. Вещь, которая на самом деле лежит на поверхности. Но иногда нам полезно о ней напоминать. А то, что прежде всего мы инженеры, и мы решаем с вами инженерную задачу. И программный комплекс SOFiSTiK, он позволяет нам в значительной степени сократить затраты, в значительной степени сократить денежные средства и время на выполнение наших инженерных задач. Итак, следующая секция будет полностью посвящена мостам. Пожалуйста, давайте отдохнем. Так, кофе-брейк.